Could everything you know be torn apart? This is not a question about a single star or galaxy, but about the entire cosmos and its ultimate fate. Scientists call this terrifying possibility the Big Rip scenario, a hypothesis where the very fabric of space-time stretches until every single structure, down to the atoms that make you, is ripped to shreds. By the end of this exploration, you will understand 30 distinct theories that explain how and why our universe might meet such a dramatic end. We will investigate why dark energy could turn against us, and whether the laws of physics themselves might offer a last-minute escape. What do you believe is waiting for us at the end of time? This terrifying vision of cosmic destruction begins with a single number. Scientists call it the equation of state parameter, represented by the letter W. For the universe to remain stable, this number needs to be greater than -1. But what if it is not? Theory 1, the phantom energy dominance theory, proposes that a specific, aggressive form of dark energy exists, one where W is less than -1. This is phantom energy, and its existence would fundamentally break the rules of cosmic stability. Unlike the gentle push of a cosmological constant, phantom energy would cause the expansion of the universe to accelerate at a rate that itself increases over time. It is an unstoppable feedback loop of growth. The key consequence is a change in the Hubble constant, the rate at which the universe expands. Instead of holding steady, the Hubble constant would begin to climb faster and faster as phantom energy takes complete control. The first signs of doom would be subtle. The immense gravitational glue holding clusters of galaxies together would be the first to fail. These vast families of stars, bound for billions of years, would be violently pulled apart, their members flung into the ever-widening emptiness. Next, individual galaxies would be shredded. The Milky Way and Andromeda, destined for a future collision, would instead see the space between them expand so rapidly that their stars are torn from their galactic orbits. Solar systems would be next, with planets ripped away from their suns. Finally, in the last fleeting moments, the phantom energy field would become so powerful that it would overcome the very forces holding matter together. The bonds between atoms would snap, then the atomic nuclei themselves would be torn apart, dissolving all physical structure into a thin, cold mist of fundamental particles. This radical idea was formally proposed in a paper by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in 2003. The initial reception in the cosmology community was a mixture of fascination and deep skepticism, as it challenged the most fundamental assumptions about how our universe must end. That initial proposal of phantom energy was a stark and simple warning, but the cosmos rarely deals in simple answers. A more nuanced possibility exists, one where the destructive force is not a constant, but something that changes and grows. This is Theory 2, the Quintessence Field model. It suggests that dark energy is not a fixed feature of empty space, but a dynamic, evolving field that permeates the entire universe. Scientists call this field quintessence, a name borrowed from an ancient term for a fifth fundamental element. Unlike the rigid cosmological constant, which gives dark energy a steady, unchanging strength, quintessence is a scalar field. This means its energy density and its pressure can change over time, influenced by its own unique potential energy landscape. Think of it like a ball rolling across a complex, undulating surface. The shape of that surface, the hills and valleys, dictates how the ball moves and how much energy it has. Certain theoretical shapes for this quintessence potential could cause the field to evolve in a very specific and terrifying way. The ball could start rolling down a slope that becomes increasingly steep, causing its energy to grow more and more powerful. In this scenario, the equation of state parameter, that critical W value, could cross the phantom divide, plummeting past -1. The quintessence field would then begin to exhibit phantom-like behavior, but with a key difference: its destructive power would not have been there from the start. It would have developed it as if the universe itself cultivated the seeds of its own destruction. This offers a more flexible framework for understanding our fate. Instead of a universe doomed from its first moments by a fixed constant, we could be living in a cosmos where the fate is still being written by the evolving dynamics of this mysterious field. The question then becomes, what kind of hill is our universe rolling down, and is the bottom a cliff into nothingness? The Quintessence Field presents a slow, cultivated march toward oblivion. Yet another theory argues the end will not come with a slow crescendo, but with a single, shocking crack. Theory 3, the sudden future singularity hypothesis, proposes a radically different path to destruction. In this model, the universe does not tear itself apart over billions of years. It ends in a single, finite moment, a cosmic snap where the very rules of physics cease to apply. The key difference lies in what happens to the scale factor of the universe, a measure of how much the cosmos has stretched since the Big Bang. In the classic Big Rip, this expansion accelerates forever, gradually overwhelming all forces. In a sudden future singularity, the expansion rate itself does not necessarily run to infinity. Instead, something far stranger occurs. The density of the universe and its pressure violently diverge, rocketing toward infinity in a flash. It would be as if you were driving a car that was smoothly accelerating, and then, without any further change in the engine's power, the car and everything inside it was instantly and utterly annihilated. The conditions for this require a specific and bizarre breakdown in the relationship between the universe's contents and the geometry of space-time itself. For this to happen, a form of dark energy would need to exert a pressure that becomes infinite, even while the expansion rate of the universe remains finite. This creates a fundamental rupture in the fabric of reality, a true singularity not in the distant past like the Big Bang, but waiting for us in the future. One moment the cosmos exists, the next every star, planet, and atom is gone, not torn asunder, but erased in an instantaneous, incomprehensible flash. Each of these theories presents a final, finite moment for reality. But what if the end of everything is not an event you can point to on a cosmic calendar? Theory 4, the Little Rip alternative, offers a far more gradual and perhaps more chilling finale. In this model, the universe still expands and accelerates, driven by a powerful form of dark energy. Bound structures are still torn apart, from galaxy clusters down to planets and atoms. The destruction is just as total and complete as in the Big Rip. The crucial difference lies in the timeline. The Little Rip avoids a future singularity, a specific point in time where the universe's density and pressure become infinite. Instead, the tearing happens asymptotically over an infinite future. This means the destructive force grows powerful enough to shred everything, but it never quite becomes infinite at any finite time. There is no final, catastrophic snap. The universe simply unravels forever. Imagine trying to tear a piece of incredibly strong fabric. In the classic Big Rip, you pull with a force that becomes infinite, and the fabric instantly vaporizes at a precise moment. In the Little Rip, you pull with a force that always increases, getting stronger and stronger without ever reaching an infinite value. The fabric still tears, but the process takes an eternity, with the last thread stretching into an endless, silent void. Physically, this changes the experience of the end. A planet would not be violently ripped from its star in a flash. The gravitational bond would be stretched over eons, a slow, agonizing drift into absolute isolation. The final stars would not explode, they would simply fade and cool, their light stretched into useless, long wavelengths as space itself pulled them apart. For some cosmologists, this model is more plausible because it avoids the mathematical and physical paradoxes of a true singularity in our future. The laws of physics, though pushed to their absolute limits, never formally break. They just preside over an endless, cold, and empty dissolution. The question then becomes, is an eternity of slow unraveling a more terrifying fate than a single sudden end? A slow, steady unraveling may be the cosmos's most likely fate, but what if the end is not a dramatic tear, but a quiet, inexorable drift into solitude? Theory 5, the pseudo-rip-scenario, offers this unsettlingly gentle apocalypse. Here, the phantom energy driving the expansion does not run away to infinity. Instead, the expansion rate and the Hubble parameter, the value that measures how fast the universe is stretching, approach a constant, steady state. This is similar to the De Sitter universe, an idealized model of eternal, empty expansion driven by a cosmological constant. But in the pseudo-rip, this state is an illusion, a temporary plateau on a much longer, slower climb. The phantom energy still causes a slow, steady increase in the Hubble parameter, so faint it is almost imperceptible over billions of years. This tiny, relentless push is what makes all the difference. It means that while the universe will not be shredded in a final, violent instant, it will still be pulled apart over an extremely long, but ultimately finite timescale. The first and most profound effect would be the isolation of cosmic horizons. Every observer in the universe has a cosmic horizon, a boundary beyond which light can never reach them because the space between is expanding too quickly. In the pseudo-rip, these horizons would slowly but surely shrink. Galaxies that are visible in our night sky today would, one by one, cross our horizon and disappear, their light stretched beyond detection as the space between us becomes an unbridgeable gulf. We would not see them explode or fade. They would simply vanish from the universe as if a silent, dark curtain were being drawn across the cosmos. This would lead to a fate that resembles the classic heat death, a state of maximum isolation and cold. Long before any atoms are ripped apart, the universe would have become a collection of isolated galaxy clusters, then individual galaxies, and finally solitary star systems, each trapped within its own lonely pocket of reality, unable to see or interact with anything else. The final rip, the dissolution of atoms, would only occur after an almost unimaginable duration, long after the universe has become a ghost of its former self. In this scenario, the end is not a bang nor a rip, but a slow, silent goodbye to everything we have ever known. This single number, W, holds the key to our entire cosmic future. It is the equation of state parameter, a deceptively simple value that describes the relationship between the pressure and density of dark energy. To understand it, picture a gas inside a piston. When you compress the gas, it pushes back with a certain pressure. The number W tells us how hard dark energy pushes back as the universe expands and stretches it. For normal matter and radiation, this value is positive or zero. But for dark energy, it is negative, and that negative pressure is what drives the cosmic acceleration. The precise value of W is what separates a slow heat death from a violent, absolute end. If W is greater than -1, the universe continues to expand and accelerate, but the force of dark energy remains limited. Galaxies will drift apart, stars will burn out, and the cosmos will approach a cold, dark, and isolated state known as the Big Freeze or heat death. This is a slow, quiet fade into nothingness. If W is exactly equal to -1, we live in a De Sitter universe named after the physicist Willem de Sitter. In this model, the expansion is driven by a cosmological constant, a steady, unchanging force. The acceleration continues forever at a constant rate, leading again to an eventual big freeze, a vast, empty, and eternal expanse. But if W is less than -1, even by the tiniest fraction, the outcome is utterly different. This is the phantom energy regime, and it guarantees a big rip. The negative pressure of dark energy becomes so extreme that it causes the expansion to accelerate at an ever-increasing rate. A runaway effect that eventually overcomes every force in the universe, from gravity to the nuclear bonds holding atoms together. Current observations from powerful missions like the Planck satellite have been trying to measure W with incredible precision. The best data we have suggests that W is very close to -1, consistent with a simple cosmological constant. But the error bars, the range of uncertainty, have not yet completely ruled out a value slightly below -1. Our fate currently hangs in the balance, suspended within a margin of error in a scientific dataset. The profound implication is that the ultimate destiny of every galaxy, star, planet, and atom could be decided by a number so small it is currently lost in the noise of our measurements. String theory offers a stage for the most dramatic cosmic endings. Our universe might not be an isolated expanse, but a three-dimensional membrane or brain, adrift in a higher dimensional space called the bulk. This is Theory 7, the brain cosmology rip, and it rewrites the entire script for how our world could be torn apart. In this framework, the dark energy driving the expansion could be a side effect of fundamental interactions between our brain and the hidden dimensions around us. The force we perceive as cosmic acceleration might not be an intrinsic property of our space, but a shadow of something much larger and more violent happening in the bulk. One terrifying possibility is a collision with another brain. Picture two vast, invisible sheets floating in a higher dimensional ocean, slowly drifting toward one another. Their impact would release an unimaginable surge of energy across our entire universe, a shockwave of expansion that could easily mimic or directly cause a big rip event. The energy injection would be so sudden and so uniform that it would instantly overwhelm all binding forces, shredding the cosmos from the top down. Another mechanism involves gravity itself slowly bleeding away. In some brain world models, the graviton, the hypothetical particle that carries the gravitational force, is not perfectly confined to our brain. It can leak out into the bulk. Over cosmic timescales, this subtle leakage could lead to a slow but steady modification of gravity on the largest scales. The effective strength of gravity holding the universe together would appear to weaken, not because dark energy is pushing, but because the fundamental glue of the cosmos is slowly dissipating into higher dimensions. This weakening could accelerate the expansion in a way that perfectly mimics phantom energy, leading to the same catastrophic unraveling. The profound implication here is that the Big Rip may not be a story about a single universe dying from within. It could be the final act in a much larger, multidimensional drama, where our fate is sealed by forces and entities we cannot even perceive. Perhaps the universe prefers elegant simplicity over a menagerie of mysterious components. Theory 8, the Chaplygin gas model, offers a radical proposal, suggesting that dark matter and dark energy are not two separate, unknown substances, but different manifestations of a single, exotic fluid permeating the cosmos. This hypothetical entity is named for a Russian physicist who studied a certain type of fluid in aerodynamics, but its cosmic application is far grander. In its earliest form, this Chaplygin gas behaves just like cold dark matter. Its particles clump together under gravity, providing the scaffolding upon which galaxies and galaxy clusters can form. Without this initial gravitational glue, the universe would never have developed the structure we see today. But as the universe expands, this fluid undergoes a remarkable transformation. Its equation of state, that critical W value, begins to change. It slowly evolves from acting like pressureless matter to behaving more and more like a cosmological constant, the steady force driving cosmic acceleration. This single fluid can therefore explain both the structure formation of the early universe and its accelerated expansion today. It is a beautifully unified picture. However, the story does not end there. Specific, more complex variants of the Chaplygin gas model introduce a terrifying twist. In these scenarios, the evolution of the fluid does not stop at mimicking a simple cosmological constant. Instead, its pressure can continue to become more negative, pushing its W value across the phantom divide, plummeting past -1. The very substance that once acted as the cosmic glue, holding everything together, would then transform into a phantom energy capable of triggering a late-time Big Rip. The universe would be torn apart by the same fundamental entity that once built it. This presents a profound and unsettling irony. The cosmic architect becomes the cosmic executioner. The appeal of this unified approach is immense, as it elegantly reduces two of the greatest mysteries in physics down to one. Yet it faces significant theoretical challenges, particularly in explaining the precise details of how galaxies form and rotate, areas where pure dark matter models have been very successful. The question this theory forces us to ask is whether the cosmos is built on a foundation of duality, with separate forces for creation and destruction, or if it is all the work of a single, chameleonic entity whose ultimate purpose is to both build and unbuild everything we know. Could the ultimate destruction be a prelude to a new creation? This is the core of Theory 9, which places the Big Rip within a grand cosmic cycle. Cyclic models of the universe propose an eternal rhythm, where a phase of expansion is always followed by a contraction into a big crunch, which then rebounds into a new Big Bang. But what if the violent expansion of a Big Rip is not the final curtain, but the very mechanism that triggers the next cosmic dawn? In this framework, the rip serves as the ultimate cosmic reset. As phantom energy tears apart every atom and nucleus, dissolving all structure into a uniform sea of fundamental particles, it also erases all information, all order, and all traces of the previous universe. The cosmos is returned to a state of maximum simplicity and uniformity, a blank slate. Some theorists suggest that this state of extreme, empty expansion could become unstable. The phantom energy field, having accomplished its destructive work, might decay or transform. This transformation could release an immense amount of potential energy, effectively creating a new fireball of radiation and matter, a seed for a new Big Bang. In this breathtaking vision, the rip is not an end. It is a violent, necessary cleansing that prepares the stage for a fresh start. The endless cycle of creation and destruction becomes a single, continuous process, with the Big Rip as the dramatic turning point. One universe dies so that another can be born from its ashes, in an infinite loop without beginning or end. The holographic principle suggests our three-dimensional reality might be a projection from a two-dimensional surface at its boundary. Every star, every person, every event is encoded on this distant cosmic film. As the universe expands toward a rip, this foundational idea confronts a terrifying paradox. The amount of information the cosmos can hold is not proportional to its volume, but to the area of its boundary surface. In a universe racing toward a Big Rip, that surface area is shrinking relative to the volume it contains. The cosmic horizon, the effective boundary of our observable universe, is relentlessly closing in. This means the total information capacity of the universe is plummeting. Long before phantom energy begins to tear apart galaxies, the cosmos would face an information crisis. There would simply not be enough room on the shrinking boundary to encode the vast complexity of everything within. It is like trying to store the entire contents of a massive library on a single, ever-shrinking memory chip. The information must go somewhere. Would the laws of physics begin to glitch, erasing complex structures to free up information space? Would planets, stars, and even memories simply fade from existence not from force, but from a fundamental lack of space to be written down? This information bottleneck could cause reality itself to destabilize long before the final rip, presenting a paradox that challenges our very understanding of what exists and what it means to be real. Our cosmic fate may be decided by a hidden dialogue between its two most dominant players. Theory 11 explores a profound possibility that dark energy and dark matter are not isolated entities but are locked in a secret exchange. Most models treat them as separate, one clumping under gravity and the other driving expansion. But what if they are connected by a fundamental interaction, a conduit that allows energy to flow directly from one to the other? In this dynamic relationship, dark matter could be slowly feeding its energy into dark energy. Imagine a reservoir of water slowly draining into a growing, powerful river. The reservoir represents dark matter whose gravitational pull helps hold the cosmos together. The river is dark energy, the force pushing everything apart. As energy transfers from the reservoir to the river swells and accelerates. This energy transfer would have a direct and terrifying consequence. It would cause the strength of dark energy to grow over cosmic time. This amplification would not be a gentle nudge. It would actively push the equation of state parameter, that critical W value, further into the negative, potentially driving it across the phantom divide to a value less than -1. A universe that might have been headed for a gentle freeze could be pushed inexorably toward a violent rip, all because of this hidden conversation between its primary components. This interaction makes a big rip far more likely, even if the intrinsic nature of dark energy is not phantom-like on its own. Its destructive power is cultivated and amplified by its cosmic partner. The observational hunt for this interaction is already underway. Astronomers search for subtle discrepancies in the large-scale structure of the universe. If dark matter is slowly losing energy, its ability to clump and form the cosmic web of galaxies would be subtly impaired over billions of years. By mapping the distribution of galaxies across vast distances and back in time, we might detect a telltale sign that this energy transfer is happening. Another signature lies in the cosmic microwave background, the afterglow of the Big Bang. The precise patterns in this ancient light are exquisitely sensitive to the balance between matter and energy in the cosmos. An interaction between dark matter and dark energy would leave a unique fingerprint on these patterns, a small but measurable deviation from the predictions of standard models. Finding such evidence would not just confirm a new physical process, it would fundamentally rewrite our forecast for the end of everything, revealing a universe tearing itself apart from the inside out through a partnership we are only beginning to understand. Even the most formidable prisons in the cosmos have a scheduled demolition date. Black holes, those regions of space-time where gravity is so intense that not even light can escape, are often thought of as eternal. But in the final act of a big rip, their immortality is a fragile illusion. As phantom energy drives the universe's accelerating expansion, a profound reversal occurs. The cosmological horizon, the boundary of the observable universe, begins to shrink inward at an ever-increasing rate. Meanwhile, a black hole's event horizon, the point of no return, is a fixed size dictated by its mass. In the rip's final stages, the phantom energy density surges toward infinity, and the shrinking cosmic horizon will eventually become smaller than the event horizons of all black holes. When this happens, the black hole is effectively left outside the observable universe, isolated in a void where the fabric of space-time is stretching apart faster than the hole's gravitational pull can maintain its integrity. The sequence of destruction is as methodical as it is terrifying. First, the phantom energy would sever a black hole from the rest of the cosmos. No new matter or energy could fall in, starving it of sustenance. Then, the intense stretching of space would begin to distort the event horizon itself. The gravitational bonds that hold the singularity in check would be overwhelmed by the colossal outward pressure. In a final, spectacular release, the black hole would not just evaporate slowly as Stephen Hawking once theorized, it would be violently dismantled. Its entire mass energy would be unleashed in a flash, a last moment of cosmic fury before space-time itself is shredded down to the subatomic level. This means that in the universe's last moments, not even the darkest, most powerful objects would remain. The rip cleans the slate with absolute finality, leaving no relic, no monument, not even a black hole to mark what once was. This relentless march toward annihilation seems absolute, but the universe may have one last card to play. Theory 13, the quantum gravity save, argues that the very physics of the Big Rip would trigger its own salvation. The core of the problem lies in the singularity, a point where density and pressure become infinite and our known laws of physics break down. We face a similar problem at the moment of the Big Bang, another singularity where classical physics fails. This is where quantum gravity must take over. Quantum gravity is the long-sought theory that aims to unite Einstein's general relativity, which governs the very large with quantum mechanics, the rules of the very small. At the extreme energies and minute scales that would characterize the final moments of a Big Rip, these quantum effects would become dominant, and they could fundamentally alter the outcome. One promising candidate is loop quantum cosmology. This theory suggests that space itself is not a smooth, continuous fabric, but is woven from tiny, finite loops, a fabric with a fundamental graininess. This granular structure imposes a limit on how much space can be curved or stretched. As phantom energy tries to drive the universe toward an infinite density, the quantum geometry of loop quantum cosmology would provide a powerful repulsive force. Instead of ripping apart, the universe would hit a quantum wall and bounce. The catastrophic expansion would reverse into a contraction, potentially birthing a new cosmic cycle without ever reaching the point of total dissolution. Another possibility comes from string gas cosmology based on string theory. In this model, the universe's fundamental constituents are not point particles but tiny, vibrating strings. As the universe nears a rip state, the behavior of this stringy gas could prevent a true singularity. The string's vibrational modes and winding energies around compact dimensions could create a stabilizing pressure, halting the runaway expansion and leading to a new phase. The profound implication is that the universe might possess a fundamental self-preservation instinct written into the code of quantum spacetime. The very act of stretching reality to its absolute limit would activate a safety mechanism, a cosmic bounce that transforms the end into a new beginning. So the ultimate question shifts. We must ask not only if the universe will end, but whether the laws of physics themselves forbid a final, silent nothingness. Every fundamental constant we rely on could be a temporary variable. The speed of light, c, is the ultimate cosmic speed limit, a seemingly immutable pillar upon which all of modern physics is built. But what if this constant is not so constant after all? Theory 14, the varying speed of light rip, dares to challenge this foundation. This controversial idea suggests that the speed of light was not always the same number we measure today. In the extreme density of the early universe, light may have traveled vastly faster, a hypothesis that could solve several major puzzles in cosmology. If the speed of light can change once, it could potentially change again, and its future evolution could directly dictate our cosmic fate. The equations that describe the universe's expansion, the Friedmann equations, are deeply woven with the speed of light. It appears in the constants governing gravity, the energy density of radiation, and the very geometry of spacetime. If c were to begin decreasing in the far future, the consequences would be as profound as they are bizarre. The strength of gravity, for instance, is tied to c. A slower speed of light could effectively weaken the gravitational constant, reducing the cosmic glue that holds galaxies and clusters together. This would mimic the effect of a strengthening dark energy, potentially accelerating the expansion enough to trigger a big rip, even if dark energy itself remained benign. Conversely, an increasing speed of light could have the opposite effect, strengthening gravity and applying a brake to the universe's expansion, perhaps even pulling everything back together in a big crunch. The mechanism behind such a change is deeply speculative. It could be tied to the evolution of the vacuum itself, or to a fundamental scalar field that governs the values of nature's constants over cosmic time. The implications shatter our understanding of reality. A universe with a varying C is a universe where the laws of physics are not fixed, but are evolving along with the cosmos they describe. The reliability of our scientific knowledge, built on experiments conducted over a mere sliver of cosmic time, would be thrown into question. The ultimate fate of everything might not be written in the value of dark energy's W, but in the silent, imperceptible drift of a number we thought was forever locked in place. The end of the universe could feel less like a violent shredding and more like a cosmic pot reaching its boiling point. This is the unsettling vision of Theory 15, the Big Rip as a phase transition. We are familiar with phase transitions in everyday life. The moment water absorbs enough heat to transform into steam, the liquid state with its cohesive bonds suddenly gives way to a gaseous state where molecules fly apart. Our universe could be approaching a similar tipping point, driven not by heat, but by the relentless accumulation of vacuum energy. The phantom energy saturating the cosmos would act like a cosmic stove, steadily increasing its output until the very fabric of space-time can no longer maintain its current state. The vacuum we perceive as stable and empty is not truly empty. It seethes with quantum fluctuations and latent energy. As dark energy dominates, this vacuum could become unstable, poised to decay into a lower, more stable energy state. When that critical threshold is crossed, the transition would not be a slow unraveling, but a sudden, spontaneous event that rewrites reality itself. Space-time would effectively boil, with bubbles of this new, true vacuum nucleating and expanding at the speed of light. Within these bubbles, the fundamental constants of nature, the strength of forces, and even the number of spatial dimensions could be completely different. The rip would not be a mechanical tearing by an external force, but an internal transformation of the cosmos's very substance. One moment, you have a universe governed by familiar physics with atoms, stars, and life. The next, a wave of new physics sweeps through, and in its wake, the concept of an atom or a planet no longer has any meaning. The old reality simply ceases to be, replaced by something entirely alien. This idea forces us to confront a profound question. Is our entire existence, with all its laws and structure, merely a temporary, metastable state, a delicate balance that phantom energy is destined to shatter, pouring our universe into a new and unknown form? Could the ghostly neutrinos streaming through your body right now be agents of the apocalypse? These tiny, nearly massless particles are cosmic phantoms, produced in abundance by the sun and distant supernova, trillions of which pass through you every second without a trace. Their ethereal nature has always made them difficult to study, but Theory 16 suggests they may play a far more active role in our fate than anyone suspected. The key lies in a potential secret interaction between these elusive particles and the quintessence field, the dynamic form of dark energy. Imagine a vast, invisible field of energy that fills the cosmos and a near-infinite swarm of ghost particles constantly moving through it. Most models assume they ignore each other, but what if they do not? A coupling could exist, a fundamental link where the presence and behavior of neutrinos subtly influences the quintessence field. As the universe expands and cools, neutrinos, which have a very small but non-zero mass, begin to slow down. They transition from moving at nearly the speed of light to moving more slowly, becoming what physicists call non-relativistic. This shift in their behavior could be the trigger. When the neutrinos are relativistic, their high energy might stabilize the quintessence field. But as they slow, their effective pressure drops, and this change could resonate through the coupling. It would be like removing a stabilizing weight from a delicate scale. The quintessence field, no longer held in check, could plunge down its potential energy slope, its energy density beginning to climb rapidly. This is the instability that seals our fate. The interaction would actively drive the equation of state parameter, that critical W value, downward, pushing it across the phantom divide to less than -1. In this scenario, neutrinos become an unexpected catalyst. They are not the fuel for destruction, but the spark that ignites it. The very act of these ghost particles cooling down and becoming more sedate in an expanding universe could be the signal that flips the quintessence field into its phantom mode, setting the stage for the final, catastrophic expansion. It is a profound connection between the world of the very small and the ultimate fate of the very large, suggesting that the seeds of cosmic destruction are woven into the fabric of the particle world we are still struggling to see. Perhaps our universe's destruction is a necessary prelude to a cosmic rebirth. Theory 17, the ekpyrotic universe and the rip, weaves the Big Rip into a stunning cyclical narrative where the end is not a finality, but a violent reset triggered by a collision in a higher dimensional reality. The ekpyrotic model envisions our four-dimensional universe as a three-dimensional brain, one of many floating in a vast bulk. In this grand cosmic dance, our brain is on a slow, inevitable collision course with a neighboring brain, a parallel universe separated from us by an unseen dimension. As these two titanic membranes approach one another, the potential energy between them builds to an unimaginable crescendo. This is where the rip finds its role. The immense energy released in the moments just before the collision could flood our brain, manifesting as a sudden and overwhelming surge of phantom energy. The effect would be a rapid, rip-like expansion that tears apart every structure in our cosmos. Galaxies, stars, and atoms are all shredded into a uniform, high-energy plasma in the final instance before the impact. This violent dissolution serves a profound purpose. It erases all the complex structure and information of the old cycle, wiping the cosmic slate completely clean. Then the collision itself occurs. The kinetic energy of the brains smashing together is converted into a fireball of radiation and matter, effectively creating a new hot Big Bang from the ashes of the old, ripped-apart universe. In this breathtaking synthesis, the Big Rip is not a lonely end. It is the dramatic climax of one cycle and the essential catalyst for the next, a necessary purification that allows the cosmos to be born again and again in an eternal, rhythmic loop of creation and destruction. The universe's final moments would be a thermodynamic paradox. The second law of thermodynamics states that entropy, a measure of disorder, always increases in an isolated system. Our cosmos has been on this one-way street toward maximum disorder since the Big Bang, with stars burning out and galaxies scattering. But the Big Rip presents a bizarre and violent twist on this journey. As phantom energy accelerates the expansion, it does not just increase disorder, it actively dismantles the very systems that can have disorder. Think of a sand castle on a beach. Over time, wind and waves increase its entropy, breaking it down into a random pile of sand. This is the classic heat death. Now imagine a tsunami so powerful it does not just scatter the sandcastle, it scatters every single grain of sand so far apart that they can never interact again. This is the rip. In this scenario, the universe is not reaching a state of high entropy, it is achieving a state of profound, absolute isolation. With every atom separated by an infinite gulf of expanding space, there are no longer any temperature differences, no energy flows, and no structures to break down. The cosmos becomes a perfect, uniform, and utterly static void. From a thermodynamic perspective, this could be interpreted as the ultimate maximum entropy, a state where nothing can ever happen again. Yet, this final state is strangely orderly, a cold and empty perfection that is the opposite of a messy, high-energy chaos. This leads to a profound question. Does the rip represent the final victory of entropy, or does it, paradoxically, reset the clock? By tearing apart every structure and erasing all information, the Big Rip could be creating a new, pristine, low-entropy state. A universe with all matter dissolved into a uniform mist and all energy diluted by infinite space is a blank canvas. It is a state of such simplicity that it could, in theory, be the starting point for a new cosmic cycle, a new Big Bang born from the ashes of absolute dissolution. The end of everything might not be an eternal prison of disorder, but the quiet before the next storm of creation. Einstein's theory of gravity is a masterpiece, but it may not be the final word. Theory 19 asks what happens if gravity itself is different on cosmic scales. This is the realm of F of R gravity, a class of theories where the rules of space-time are rewritten. In Einstein's general relativity, the fabric of the cosmos is shaped by a specific mathematical term called the Ricci scalar, denoted by R. It is a measure of how space-time is curved by the matter and energy within it. F of R gravity proposes a radical change. It suggests that the fundamental action of the universe, the very core of its gravitational law, is not simply R, but a more complex function of R. This single change unlocks a universe of possibilities. Specific, carefully chosen forms of this F of R function can produce a remarkable effect. They can generate the accelerated expansion of the universe purely from geometry, with no need for dark energy at all. The empty vacuum of space, with its intrinsic curvature, could be pushing itself apart. In these models, the phantom behavior needed for a big rip does not come from an exotic substance with negative pressure. Instead, it emerges naturally from the modified geometric terms in the equations. The function f of r effectively acts as a cosmic driver, commanding space-time to stretch with an ever-increasing ferocity. One could imagine a sheet of rubber that does not just stretch when you pull it, but begins to pull on itself, accelerating its own expansion until it tears. That self-amplifying stretch is what certain f of r geometries can accomplish. This transforms our search for the end. We are no longer just hunting for a mysterious dark energy component. We are questioning the very nature of gravity and the geometry of reality. Could the force that builds galaxies and holds planets in orbit contain, in its deepest mathematical structure, the seeds of its own ultimate undoing, a self-destruct mechanism written into the code of spacetime itself? The hunt for the rip's cause leads us back to the first force we ever knew and asks if we have truly understood it at all. A fundamental rule of our universe might be broken in its final seconds. The cosmic censorship hypothesis proposed by the physicist Roger Penrose argues that nature abhors a naked singularity. It is the idea that every singularity, a point of infinite density where the laws of physics break down, must be hidden from view behind an event horizon like the one cloaking a black hole. This cosmic curtain ensures that the unpredictable chaos of the singularity cannot affect the outside universe, preserving our ability to predict the future based on known physics. The Big Rip presents a direct challenge to this sacred principle. In that final, finite moment, a singularity occurs not in the hidden heart of a black hole, but everywhere at once. Every point in space becomes a point where density and pressure race toward infinity. There is no event horizon to form a protective shield because the singularity is global, affecting all observers simultaneously. This creates the ultimate naked singularity, a breakdown of physics laid bare across the entire cosmos. What would this mean for the predictability of the universe in its last moments? The equations we use to describe reality would simply give nonsensical answers, infinite values that render forecasting impossible. The orderly chain of cause and effect, the very foundation of science, would shatter. One moment, the universe is expanding according to a set of rules. The next, those rules evaporate and anything could happen. Perhaps new laws of physics would spontaneously emerge from the chaos, governing the transition into absolute nothingness. Or perhaps the universe would simply cease to be calculable, its final state forever unknown and unknowable. The existence of a big rip singularity would not just be an end to matter, but an end to physics itself, a final, defiant act of cosmic lawlessness. Our cosmic fate might not be written by any law, but by a simple, chilling roll of the dice. Theory 21, the multiverse selection theory, suggests our universe is just one member of an infinite ensemble, a single bubble in a vast cosmic foam where every possible set of physical laws is realized somewhere. In this grand panorama, the value of dark energy density is not a unique, finely tuned number, but a random variable. Some universes have so much dark energy they rip apart instantly after their Big Bang, never forming a single star. Others have so little that they collapse back into a big crunch after only a brief existence. Our universe appears to occupy a middle ground, with just enough dark energy to drive acceleration, but not so much that it destroyed us before life could arise. This is the anthropic principle in action, a statistical filter on what we can observe. We could not find ourselves in a universe that is already dead, so we naturally observe one that has lasted long enough for us to be here. However, this comfortable middle ground may be an illusion. The range of dark energy densities that allow for galaxies, stars, and planets to form is actually quite narrow. But the range that permits a late-time Big Rip is much, much wider. It is statistically far more likely for a random universe to have a dark energy density high enough to eventually cause a rip than to have the perfectly balanced value needed for a slow, eternal heat death. Our doomed fate, then, might have no deeper meaning. We are not special, we are just probable. We happen to live in a universe whose randomly assigned ticket has a rip printed on the back, a common outcome in a multiverse where most stories end with a violent final tear. This idea transforms the Big Rip from a terrifying mystery into a mundane statistical certainty, the most likely ending for a universe like ours in a cosmos where everything that can happen does happen for no reason at all. Our universe appears beautifully uniform in every direction, a cornerstone principle of modern cosmology. Yet a stubborn anomaly in the oldest light we can see challenges this perfect symmetry. Scientists call it the axis of evil, a mysterious, large-scale alignment in the patterns of the cosmic microwave background. This is not a demonic presence, but a statistical oddity so significant and unsettling that it earned its dramatic name. The hot and cold spots in this primordial afterglow seem to be aligned along a particular plane in the sky, a preferred direction that should not exist in a truly isotropic cosmos. Most models dismiss it as a cosmic fluke, a trick of the data, but Theory 22 dares to ask a more terrifying question. What if the axis of evil is not a fluke at all, but the first visible symptom of a deep, fundamental lopsidedness in the force destined to destroy everything? This would mean the dark energy driving the expansion is not the same in all directions. It could be an anisotropic field, stronger along one cosmic axis and weaker along another. In such a universe, the phantom energy would not take hold uniformly. The rip would not happen everywhere at once. Instead, the end would come from a specific direction in space, a lopsided apocalypse. One hemisphere of the cosmos might begin to unravel first, its galaxies torn apart while the other side still holds together. The fabric of space-time would stretch thin along the axis of greatest dark energy strength, creating a directional tear that races across the universe. Imagine a piece of fabric being pulled much harder from one side than the other. It would not stretch evenly, it would distort and then shred starting from the point of greatest stress. This is what an anisotropic Big Rip could look like on a cosmic scale. For observers in a galaxy caught in the path of the advancing rip front, the sky would tell a horrifying story. One half of the heavens would show distant galaxy clusters violently flying apart, their light stretched and distorted, while the other half might appear deceptively normal for a little while longer. The universe would die not with a synchronized snap, but with a grim, directional unraveling, its final moments dictated by a hidden axis written into the first light of creation. The ultimate cosmic library is about to be burned to the ground. Every star, every planet, and every living being represents an immense volume of information, a story written in the complex arrangement of matter and energy. In a big rip, these stories are not just lost, they are systematically annihilated as atoms and nuclei are torn into their fundamental components. This presents a profound conflict with one of the most sacred principles in quantum mechanics, the law of unitarity. Unitarity is the rule that information cannot be created or destroyed, only transformed. It is the universe's ultimate accounting system, ensuring that the past always has a causal link to the future. If the rip destroys every physical system that can encode information, where does all that quantum information go? Does it simply vanish, erasing the entire history of the cosmos from existence? This is the information paradox of the rip, a crisis that threatens the logical foundation of physics itself. Some theorists propose a desperate solution, that in the final, singular moment of the rip, all the information of the universe becomes encoded on the surface of the final singularity itself. It would be a last-minute, frantic etching of every bit of cosmic data onto the very point where physics breaks down. This is akin to a sinking ship's captain scribbling the ship's manifest onto the hull just as it slips beneath the waves, a final, permanent record in a place no one can ever reach. Another, even more radical idea suggests that information is not stored on the singularity, but is somehow imprinted onto the fabric of space-time as it stretches toward infinity. The ripping process would not destroy information, but would stretch and dilute it across the expanding void, transforming the intricate details of a galaxy into subtle, imperceptible wrinkles in the geometry of nothingness. The information would still exist in principle, but it would be so hopelessly scrambled and spread across an infinite volume that it could never be recovered or decoded. It would be the ultimate, irreversible erasure, not by deletion but by infinite dilution. The universe would end not with a bang or a tear, but with a whisper of data fading into a silent, featureless vacuum. The holographic universe stores our reality on a distant, two-dimensional surface. Every event, every particle is a data point encoded on this cosmic hard drive. A big rip in our three-dimensional world would be a catastrophic system failure on this foundational surface. The relentless stretching of space-time would correspond to a critical overload of information. As phantom energy drives the expansion, the volume of our universe grows, but the area of its boundary, the surface that holds all the data, remains finite or even shrinks. The cosmic hard drive is running out of space. The information describing a galaxy with its billions of stars and planets requires a vast amount of data. When the boundary can no longer store the complexity of the structure it projects, something must give. The holographic rip would manifest as a fundamental data corruption. It would not be a physical force tearing atoms apart, but a literal glitch in reality's source code. Stars might not explode, they would simply pixelate and fade, their information overwritten or deleted to free up storage. The bonds between atoms would not snap, the data defining their relationships would be erased. From our perspective inside the projection, it would look like the universe is dissolving into noise, a static fuzz where the rules of physics no longer apply. This implies a staggering truth about what we call reality. If a big rip is just a data loss on a two-dimensional surface, then our existence, with all its depth and sensation, is an incredibly complex and persistent illusion. The end of everything would not be a physical event, but the final shutdown of a cosmic simulation, a universe blinking out of existence when its foundational code can no longer be sustained. Einstein's geometric universe of curved spacetime is not the only stage upon which gravity can play out. Scalar tensor theories propose a profound addition to the cosmic drama, introducing a dynamic cosmic partner to the fabric of spacetime itself. In these frameworks, gravity is not described solely by the metric tensor, the mathematical object that defines the geometry of the cosmos. It is also influenced by a pervasive, energetic scalar field that fills the universe, a field that can change its value over time and space. The most famous of these is Brans-Dicke theory, which essentially gives the strength of gravity a dial that the scalar field can turn. Instead of Newton's constant being a fixed number, it becomes a dynamic quantity shaped by this background field. This single change rewrites the rules for the end of the universe. Within these equations, the scalar field's own energy and pressure can mimic the behavior of dark energy. More importantly, as this field evolves, its effective equation of state, that critical W parameter, can naturally evolve to cross the phantom divide. It can drop below -1 without requiring any phantom energy, ghost condensates, or other exotic substances. The phantom-like behavior emerges organically from the interplay between the scalar field and spacetime geometry. Think of it like a car accelerating not because you are pressing the gas pedal harder, but because the road itself is tilting steeper and steeper, transforming gravity from a binding force into an engine of destruction. This provides a completely different pathway to a big rip, one nestled within the very laws of gravity we thought we understood. The rip would not be caused by a mysterious anti-gravity fluid, but by the natural, terrifying evolution of gravity's own fundamental nature. The force that builds planets could, in one of its possible forms, contain the instructions for their ultimate dissolution. Our universe may be sitting on a precarious ledge, and phantom energy could be the final push that sends it over the edge. This is the unsettling intersection of the Big Rip and the Higgs vacuum metastability problem. The vacuum of space is not truly empty, it is a field of energy, and the Higgs field is what gives particles their mass. Our current understanding suggests this Higgs vacuum might not be in its most stable, lowest energy state. Instead, we could be living in a false vacuum, a temporary, metastable state, like a ball resting in a small dip on the side of a much deeper valley. For now, the ball is stable, but a large enough nudge could send it rolling down into the true vacuum at the bottom of the valley. The relentless increase in phantom energy density could provide exactly that nudge. As phantom energy builds, its immense energy density could effectively lower the barrier separating our false vacuum from the true vacuum. This makes the cosmic transition far more likely. It is like the rising tension in a stretched rubber band, making it easier to snap. The universe would not need to wait for a random quantum fluctuation to trigger the decay. The phantom energy itself could catalyze the event, causing a bubble of true vacuum to nucleate. This bubble would then expand at the speed of light, its wall rewriting the laws of physics as it passes. Inside this bubble, the fundamental constants, the strength of forces, and even the very existence of atoms as we know them would be erased. Now, imagine this vacuum decay event happening in a universe already straining under phantom energy. The result would be a double catastrophe. The vacuum decay bubble might form and begin its destructive expansion. Then, as it spreads, the phantom energy outside the bubble continues to intensify, accelerating the expansion of the remaining false vacuum. The universe would be consumed from within by a wave of new physics while simultaneously being torn apart from without by the runaway stretch of space. The two apocalyptic processes would feed into each other, creating a feedback loop of destruction that would dismantle reality faster and more thoroughly than either event could alone. The ultimate fate would not be a simple rip or a quiet decay, but a violent, simultaneous unmaking of matter and the laws that govern it, a final, irreversible erasure of the cosmos as we understand it. Our own existence might be the strongest evidence against a sudden, violent end. This is the anthropic argument against the rip, a powerful line of reasoning that uses the fact of our consciousness to place constraints on cosmic doom. The logic is starkly simple. If the Big Rip were destined to occur in, say, the next few million years, the evolution of intelligent life would be a breathtakingly unlikely coincidence. The universe is approximately 13.8 billion years old, and it has taken nearly all of that time for the first stars to form, for planets to coalesce, for the complex chemistry of life to emerge, and for a species capable of contemplating the cosmos to finally arise. The window for our evolution is incredibly narrow within the vast timeline of the cosmos. For us to appear just a geological blink before the entire universe is shredded would be a statistical miracle. The anthropic principle suggests that we should not be surprised to find ourselves living in a universe that is compatible with our existence. We could not observe a cosmos that ended before we evolved to see it. Therefore, our presence here, looking up at the stars and pondering their fate, strongly implies that any catastrophic rip does not lie in our immediate future. It pushes the apocalypse into a distant, almost abstract realm, billions or even trillions of years from now, a time frame so vast that it loses all practical terror. This argument does not disprove the Big Rip, but it powerfully reshapes its meaning. The rip might be a real destiny, but it is one waiting in such a profound distance that the entire span of human history is less than a single heartbeat in the life of the cosmos. Our universe is not necessarily safe, but it is, by its very nature, structured to allow for observers like us to have our moment in the sun before the long night falls. Our own observations of the cosmos might be weaving the fabric of its final fate. This speculative theory places the measurement problem of quantum mechanics onto the grandest stage imaginable, the entire universe. In quantum mechanics, a particle exists in a blurry cloud of possibilities, a superposition of states until it is measured, forcing it to choose a single, definite reality. What if the universe itself is governed by a similar rule? Its wave function, a mathematical description of its entire state, could exist in a superposition of possible destinies, one of which is the Big Rip. For most of cosmic history, this wave function has evolved without a definitive collapse, its potential outcomes all equally real in a quantum sense. But then, consciousness emerges, the act of observation by sentient beings, from the first creature that looked at the stars with wonder to our own detailed astronomical measurements, could be performing a constant, cumulative act of measurement on the cosmos. Each time we determine the Hubble constant or map the cosmic microwave background, we are not just passive observers, we are participants, subtly influencing which branch of reality becomes the one we experience. This leads to a staggering possibility. If the collective observations of countless civilizations across the galaxy are consistently measuring a universe that is stable and structured, we could be collectively collapsing the universal wave function away from the rip outcome. Our conscious insistence on a coherent, predictable cosmos might be actively reinforcing that very reality, steering destiny away from the phantom energy abyss. It is a cosmic version of the tree falling in the forest. If no one is there to see the universe begin to tear, does it truly rip? This idea transforms our role from mere spectators into essential actors in the cosmic story, suggesting that the ultimate fate of everything may not be written in the stars, but in the mindful act of looking up at them. A faint cosmic hum might already be echoing through the universe, carrying a message about our final destiny. This is the gravitational wave background, a sea of ripples in space-time left over from the universe's most violent beginnings. Future observatories, like a vastly evolved version of the LISA mission, are being designed to listen for this whisper. Unlike the sharp chirps from colliding black holes we detect today, this background is a stochastic signal, a collective murmur from countless cosmic events across time, all overlapping into a single faint hiss. The precise shape of this hum, its spectrum across different frequencies, is a fossil record of the universe's infancy. It holds imprints from the first moments after the Big Bang, from phase transitions when the fundamental forces split apart, and potentially from the birth of cosmic strings, theoretical defects in spacetime. The key to our fate lies in the specific signature of these primordial vibrations. If the background hum shows a particular tilt or a set of resonant peaks that cannot be explained by standard cosmic inflation, it could point toward the early existence of a phantom-like field. The same physics that governed the universe's explosive birth might have sown the seeds for its violent end, leaving a unique fingerprint in this gravitational static. Detecting this signature would be like finding a prophecy written in the vibrations of spacetime itself. It would give us an early warning, a forecast of the impending rip billions of years before the first galaxy clusters begin to strain. We would know our ultimate fate not from watching the distant galaxies recede, but from decoding a hum that has been present since the dawn of time, a final verdict delivered in a whisper from the past. A definitive end to all things forces us to confront the very purpose of existence. If every galaxy, every historical record, and every conscious thought is destined to be erased without a trace, what meaning can our brief lives possibly hold? The Big Rip offers no legacy, no cosmic memory, and no enduring monument. It is the ultimate erasure, a finality so complete it threatens to render all human striving and creativity utterly pointless when viewed against the infinite canvas of time. This is a far more absolute ending than the heat death, where the universe still exists as a cold, dark, and eternal expanse. In that slow fade, the structures we built, though cold and dead, would still exist in some form, floating in the void for an eternity. The Big Crunch offers a potential for cyclical rebirth, a cosmic phoenix rising from its own ashes, but the rip leaves nothing, not even ashes. It is a clean slate so absolute that the slate itself is destroyed. This stark finality challenges our deepest need for permanence. We build civilizations, create art, and seek knowledge in the hope that something of us will endure. The rip declares that hope an illusion, a temporary comfort in a cosmos that will ultimately forget we were ever here. Yet, this very pointlessness might be the source of a profound and liberated meaning. If nothing lasts, then the value of existence cannot lie in its endurance. It must reside entirely in the experience itself, in the fleeting, precious moments of consciousness, wonder, and connection that we share right now. The beauty of a sunset is not diminished because it ends. Its value is inherent in the experience of witnessing it. In the same way, our lives and our achievements gain their significance not from lasting forever, but from the fact that they happened at all, that in a silent and uncaring universe, a spark of awareness flickered, looked up, and for a brief moment understood something of its own strange and beautiful home. The rip does not make our story meaningless, it makes every chapter of it irreplaceable. From phantom energy's relentless push to the quantum bounce that could save us, we have journeyed across a terrifying landscape of cosmic endings. Each theory, from the multidimensional drama of brain collisions to the statistical fate dictated by the multiverse, carves a different path to the same profound dissolution. The sheer variety of these ideas reveals something fundamental. The Big Rip is less a specific prediction and more a powerful stress test for the laws of physics themselves. It forces us to question the constancy of gravity, the nature of the vacuum, and the very fabric of reality. Current data, for all its precision, points toward a quieter fate, a long, cold freeze. Yet the rip's possibility remains a vital tool, a dark lens through which we probe the universe's deepest secrets. It reminds us that our existence, for all its complexity and beauty, may be a fleeting moment in a cosmos whose ultimate rules are still being written. So we are left to wonder, in a universe that could be so transient, what meaning do we forge? Tell us in the comments which theory you find most compelling or most terrifying. Is it the silent drift of the pseudo-rip, the violent reset of the cyclic model, or the quantum save that offers a glimmer of hope beyond the end of